Hi, my name is Tom Neville, and I'm a technology manager for power electronics at Rohde & Schwarz. And today we're going to be discussing the half bridge in gate driver measurements and proper techniques when making measurements on these circuits. The half bridge is a commonly used topology across nearly every application in power electronics. The power requirements for the half bridge fit nicely with the goals of every power electronic device and system, which is to convert electrical energy efficiently, increase performance, reduce size and cost, and operate in a broad range of environmental conditions. On modern designs, the benefits of the half bridge can only be realized when the half bridge circuit, the gate drive circuit, and layout are all properly designed and optimized. In order to tune and optimize the circuit, it is critical to use proper measurement tools and techniques. This webinar will identify the most important half-bridge measurements and will offer testing methods and principles to help the designer test with greater accuracy, consistency, and reliability. Power applications will deploy different devices such as silicon MOSFETs, IGBTs, and silicon carbide MOSFETs depending on the requirements for power levels, drive methods, and operating modes. IGBTs carry a large amount of current with a low saturation voltage resulting in low conduction losses. MOSFETs also have low conduction losses which varies based on their drain to source on resistance, or RDS on. Because IGBTs carry higher current, they are used in higher power applications while MOSFETs are used in high frequency applications where high efficiency is really the key. Silicon carbide MOSFETs, while similar to silicon MOSFETs, have properties that allow them to operate at the same high power levels as IGBTs while still being able to switch at high frequencies. These properties translate into system benefits including higher power density, higher efficiency, and lower power dissipation. Optimizing the system for performance and efficiency means getting the driver and timing as close to ideal as possible. Part of the challenge to these performance gains is increasing the switching frequency. However, higher frequency may result in higher switching losses, and system design is a bigger challenge. In addition to the challenge of tuning the system, higher frequency will also likely result in more ringing, noise, and radiated emissions. Timing mismatches should be well understood, not only for increasing system performance and reducing losses, but timing failures can also lead to unfavorable events such as shoot-through. Higher frequency can also lead to negative EMI conditions. A primary industry concern for silicon carbide adoption is if it can demonstrate that it is not excessively noisy compared to silicon, and the need to demonstrate that EMI is not a limiting factor. Thus, it's critical to contain and visualize the effects of high DVDT and DIDT. And in general, most labs don't have good solutions for testing these radiated emissions, so they simply don't test for it. Additionally, it's important to characterize and understand the effects of parasitic elements and their impacts on performance, specifically device turn-on and turn-off penalties, slower performance, increased ringing noise, and EMI. It's important to characterize overshoot versus EMI performance versus losses. Level shifting is also required to raise the low current voltage PWM signals from the controller to high current voltage PWM signals to activate IGBTs. For the gate voltage, we want to ensure we don't violate the absolute maximum of the gate and ensure there is no ringing, or at least make sure it's well understood. For the half bridge, it's important to evaluate the system's performance, what's happening at the input, output, and the supply, and to see the ringing, such that the source drain voltage within the half bridge isn't violated. The ringing will be impacted by the slew rate, and a commonly used method for controlling the slew rate is through an external series gate resistor. It's important to control the rise and fall times, as these can lead to EMI issues. It's also important to properly evaluate the gate current, as it is a strength metric that determines how fast you're allowed to turn the gate on and off. Propagation delay is an important timing metric, and of particular importance is understanding the delay skew, which is difference of edges between two different channels reacting to the same input and the same operating conditions. This is important due to the timing needing to be well defined between parts or between two channels of the same part. Mismatches between parts and our poor timing can lead to shoot-through in the half bridge if the timing is too far off. Another metric is pulse width distortion, which is not the same as skew. Pulse width distortion is the difference between the rising and falling edge delays, and it can cause duty cycle variation within a given drive. A lot of times, pulse width distortion will show up on datasheets because it's easier to report. One description of skew, which I think helps understand it, is it's a variance that acts like jitter. It's also important to ensure the system is robust against noise. There are many sources of noise, including CMTI, input glitches, and RF noise in and out of the system. When possible, evaluating radiated emissions is important. Testing accomplished through proper EMI compliance testing, which will be discussed in this presentation. Accurate power measurements depend on the measurement system's performance, voltage, and current dynamic ranges, common mode rejection, connectivity, and temperature capabilities. Despite ever-increasing power design requirements, advancements in test and measurement have been minimal at best. And in some cases, this has forced designers to make custom measurement solutions or simply do without making the measurement. Tuning and optimizing the circuit requires sound measurement techniques and proper probe selection. Otherwise, designers could fall into measurement traps, which may inadvertently cause them to mistune their design. When characterizing the critical transitions in the design, users turn to a high voltage differential probe to measure the floating or high side signals, such as the high side VGS and high side VDS, the passive probe that ship with their scope for ground reference measurements, such as the low side gate, and most likely a high voltage single-ended probe for the switch node. Many times, it is the probe which has been the limiting factor in making accurate measurements. We will discuss the specifications for each of these probe types, including limitations and techniques to avoid user traps. Oscilloscopes ship standard with a set of passive probes. An oscilloscope with a standard passive probe is capable of making most of the measurements required in the half-bridge system, as long as sound measurement principles are used. When using a single-ended or ground reference passive probe, it's important to understand these probes have varying performance characteristics, voltage ranges, input impedances, and grounding solutions. A passive probe is convenient because it ships with a long ground lead, usually around 6 inches, which allows connecting to a single ground connection and probing a wide range of test points. While convenient, it's critical to understand a probe's rise time versus bandwidth, input capacitance, and ground lead inductance. Because you're connecting to ground, it's important to be aware of ground loops and learning to avoid them. A ground loop results when 2 or more separate ground paths are tied together, resulting in a loop of conductor. The current circulating in the loop develops a voltage across any impedance within the loop. Thus, ground occurs when connecting the ground lead of the probe to the ground in the device under test. In this case, the ground potential of the oscilloscope's input B and C connector is not the same as the ground in the circuit being measured. Adding an additional ground path can lead to changes in the circuit's behavior. When most people think about the measurement system's performance, they tend to look at a system's bandwidth. However, bandwidth is a frequency domain specification that defines the frequency at which the peak-to-peak amplitude of a sine wave is down 30%. Most likely, you're not interested in measuring sine waves. Most of the half-bridge measurements of interest are time domain measurements, and the measurement system specification which defines this is the rise time capability. While a rise time value can be calculated from the bandwidth, this calculation can be misleading. The only way to reliably understand the rise and fall time response of a measurement system is to measure it with a step signal that is much faster than the system to characterize it. Rohde and Schwartz uses this methodology for defining the rise time value for its products. A measurement system with insufficient rise time will have step response aberrations as shown in this example. The question then becomes, are those aberrations caused by the probe or the half-bridge? Also, measurement vendors will also peak a probe's response to improve the performance, causing overshoot and affecting the settling time. Passive probes typically include multiple grounding options. A long ground lead, usually around 6 inches, is most commonly used because you can make measurements within a 6-inch radius. While convenient, this long ground lead trades off performance and ultimately measurement uncertainty. Let's consider the possible problems that can arise from improper grounding. A passive probe can be modeled as a simple RLC circuit, and ringing at a certain frequency can be calculated and observed. It's important to understand if this ringing is from the probe or if it's due to possible EMI problems. The ring frequency is a function of the probe's ground lead and the probe's input capacitance. The probe's ground lead inductance combined with the tip capacitance and signal source capacitance forms a resonant circuit that causes ringing. A longer ground lead has more inductance and will cause the measurement to ring at a lower frequency. Some suggestions for changing the ground connection are included in the Rohde & Schwarz RTZA1 accessory set for passive probes. It includes spare spring-loaded tips, rigid tips, ground contact springs, and ground leads. Another option is the probe tip to SMA connector. If you lose your ground spring or if one isn't available, it's easy to make one using 20-gauge copper wire. You just wrap it around the probe barrel and leave wire for the measurement connection. While less convenient, using a ground spring will significantly reduce aberrations from the signal of interest. Additionally, a long ground lead can act like an antenna for noise. The long ground lead can induce hundreds of millivolts of noise, and even more as the supply voltage is increased, and in the presence of electromagnetic interference or other fast-changing signals. When evaluating gate driver performance in a half-bridge design, most people measure at the low side and ignore the high side measurement, mostly because measuring at the low side is possible because it's ground referenced and not floating, which may introduce common mode issues. When you're measuring the low side gate driver, you're looking to ensure the design is meeting specifications and if it has the characteristic waveform shape. This characteristic shape can be established using simulation. Anticipating the waveform is important to compare measured versus desired results. In general, there are three characteristic regions of the turn-on waveform that are of interest. The first is the CGS charge time. This is followed by the Miller plateau, which is the time required to change the gate drain Miller capacitance and is VDS dependent. This charge time increases as VDS increases. Once the channel is in conduction, the gate will charge to its final value. Referring back to our discussion on bandwidth and proper grounding, let's evaluate the low side gate driver's rising edge using long and short grounding techniques. Comparing the different ground accessories, the question is the noise real? Inevitably, some of the noise and ringing are real. However, as you can see in these screenshots, most of this is just measurement error. As mentioned previously, the long ground lead induces noise and ringing at a lower frequency. Swapping out the long ground with the short ground spring reduces the error-induced noise and will minimize the ringing. An alternative solution is to use a high-performance, high-voltage differential probe to minimize these effects because it has good shielding, low inductance, and high common mode rejection. Measuring non-ground reference signals, especially at the high side, can be problematic given the switch node transitioning rapidly between the supply voltage and ground. Measurements are made relative to the switch node, and this common mode signal can interfere with the ability to measure accurately. Because the high side gate is referenced to the switch node and not ground, these measurements require a differential probe. While a differential probe is the best choice for getting the difference between 2 points, it is important to understand potential limitations due to a probe's peaked step response, probe noise, common mode rejection ratio, and effects caused by the probe's long input leads. These limitations are even more pronounced when testing on power devices with fast switching rates and even nominal common mode voltage. An additional measurement that can be made with a differential probe is across the shunt resistance to get the high side current. However, care should be taken when using a differential probe in the presence of a fast, large common mode signal because the error signal is likely to swamp out the actual signal. Getting a known voltage across a shunt resistor is usually preferred to using a traditional current probe due to the added inductance of a wire needed to measure the current. When evaluating the rising and falling edges of a gate driver, users should be mindful of differential probe's rise time specification instead of its bandwidth. After all, it's a time domain measurement and it's critical to understand how accurately the probe in the oscilloscope represents the true signal in the time domain. The best method for evaluating a probe's rise time capability is to evaluate the probe's step response against the known fast high voltage reference. The step response reference signal should be ideally at least 1 kilovolt with less than 20 seconds rise time. There are 2 methods for specifying rise time that some manufacturers employ, which should cause concern for users. These 2 areas of concern are Warranting the probe's rise time using a small signal. Manufacturers that employ this method will use a small voltage step response with a fast edge for specifying the differential probe's rise time. There is typically a note in the manual that will include a disclaimer that reads something like, "Output may be slew rate limited for large amplitude signals." In short, the rise time specification is determined using a signal that's less than 20 volts, which isn't sufficient for making high voltage measurements. Another thing to look out for is some vendors will actually artificially peak the front edge to get the rated performance. In order to obtain the specified bandwidth of interest, the probe output displays a large hump at the front edge of the probe's output response. This hump is an artifact of artificially increasing the gain to boost the performance. It should be noted that the front edge of the displayed signal contains the signal's high frequency content, and manipulating this portion of the frequency will affect accuracy. By comparison, the Rohde & Schwarz ZHD series of differential probes are specified using a fast, large signal reference to determine the probe's actual rise time. This is the only true method for determining an accurate rise time specification. The signal shown in this figure is displaying the step response of a reference signal with a 1 kilovolt amplitude and a slew rate of 61 volts per nanosecond. The measured rise time of this step response is 12 nanoseconds. And the observed step response of the probes is extremely flat with negligible peaking at the front edge. Probes typically have different attenuation factors, and for a high voltage probe, for example, it might be like 10x or 100x to reduce the input signal to keep it within the operating range of the oscilloscope's front end. While attenuation extends the measurement range, the trade-off is a lower signal-to-noise ratio. An attenuator will reduce the signal by its attenuation factor, and the signal is then amplified in the oscilloscope. However, not only is the attenuated signal amplified, but so is the random probe noise, which results in a higher noise and a lower signal-to-noise ratio. A probe's noise specification is usually called out in the datasheet as input-referred noise or random noise. A probe with switchable attenuation factors will always have less noise than the probe's lower attenuation setting. When using a Rohde & Schwarz ZHD series probe, you always want to select the lower attenuation range if the signal of interest falls within the dynamic range of that setting. It's especially important to consider a probe's noise specification when measuring small signals in the presence of large common mode voltage, such as when you're measuring the high side gate driver. Common mode rejection ratio specifies the differential probe's ability to reject any signal that is common to both test points in a differential measurement. A perfect differential probe would have infinite common mode rejection across frequencies. However, traditional differential probes are fundamentally limited because it's impossible to perfectly match the inputs. The signal that is common to both the non-inverting input A and the inverting input B is referred to as the common mode signal. An ideal difference amplifier would reject 100% of the common mode signal. So using this example, if the common mode input is 1,000 volts, a perfect common mode rejection would be 1,000 minus 1,000 or 0 volts of common mode error. A differential probe's common mode rejection ratio specification is frequency dependent, and most differential probes have a common mode rejection value of 80 dB or higher at DC and low frequencies, where tuning the components accurately is more likely. At higher frequencies, however, the mismatches in the probe become increasingly harder to control, and the common mode rejection ratio specification will degrade. Consider the common mode rejection ratio versus frequency plot of a Rohde & Schwarz ZHD series of differential probes. As shown in the plot, these probes have a high common mode rejection ratio capability across bandwidth, as represented by the shaded blue area. These probes have a usable common mode rejection specification for accurately measuring the high side gate driver on most silicon MOSFETs and IGBTs, and even on some silicon carbide designs. A probe's manual typically includes a common mode rejection ratio plot versus frequency. In this example, we will calculate the common mode error for each of the device types using a traditional high voltage differential probe. So for example, an IGBT may have a switching frequency of 20 kilohertz or less, but the rise time will always be much faster. An average rise time value from the datasheets from several vendors is around 100 nanoseconds. The calculated bandwidth from 100 nanoseconds is roughly 3.5 megahertz if you use the 0.35 divided by rise time rule. It should be noted that some types of filtering equations may use values such as 0.4, but 0.35 is typically most commonly used. So from the CMRR plot, 3.5 megahertz aligns with the plot at around 57 dB of common mode rejection. Converting this value to a ratio, it's around 708 to 1. So assuming an IGBT with 1200 volts, the common mode error can be calculated as 1200 divided by 708, or 1.69 volts. So if you have a gate voltage of 20 volts, you'd have 8% measurement error. 8% would likely still provide valuable information regarding device parameters and timing characteristics. The gate current or drive strength determines how fast the device's input capacitors charge and discharge. As the gate current increases, the time to charge decreases, so you don't want the current to be too small so you don't have the losses increase. The gate driver current may be measured using a clamp-on current probe. However, this kind of current probe for this measurement can have significant drawbacks. First, a current probe requires a piece of wire to be soldered into the circuit. Adding this measurement loop will introduce additional inductance, altering the circuit's behavior. Also, current probes with sufficient bandwidth to measure faster switching devices typically have lower dynamic range. A current probe with sufficient dynamic range will most likely lack the required bandwidth. So when you're trying to measure the current, especially on the high side, many designers turn to a sense resistor instead of a current probe because the inductance from the wire loop often perturbs the circuit. Often there's already a resistor in the design in series between the gate driver and the gate. To minimize the insertion impedance in the circuit under test, the resistance of the sense resistor is kept very small, which means that the voltage drop across the sense resistor will also be very small. The current is a calculated value by taking the measured value of the voltage drop across the sense resistor and dividing it by the known resistance. The primary challenge of using a sense resistor at the high side is measuring up to hundreds of millivolts of differential voltage across the resistor riding on top of the hundreds or even thousands of volts of common mode voltage. Getting the differential voltage out of the noise at DC and low frequencies is typically possible with the differential probe. However, the limitations of the sense resistor measurements becomes more evident on the high side at higher frequencies where the probe loading starts to become more dominant on the circuit under test, and the common mode rejection ratio of the measurement system starts to decrease to a point where you can no longer determine what's the real signal across the sense resistor and what's the common mode error. Dead time is a critical timing metric in switch mode power converters, inverters, and motor drives. Dead time is the period where neither transition is being switched. Maintaining a proper dead time avoids simultaneous conduction of switchers in a half bridge. Factors affecting the dead time are pulse width distortion, propagation delay, and rise and fall times. In power systems, it's critical to maintain a minimum dead time in order to improve converter efficiency. During the dead time, current flows back through the IGBT or MOSFET body diode. Because the body diode has a much larger voltage drop than the device itself, this increases the conduction losses. The longer the dead time, the higher the losses. Therefore, it's critical to be able to accurately measure and characterize the dead time. If the drivers have tight part-to-part propagation delay matching, you can decrease the dead time without having to sacrifice efficiency or worry about safety. The preferred test method to measure the switching parameters of a MOSFET or IGBT is the double pulse test method. By looking at turn on, turn off, and reverse recovery parameters, engineers can thoroughly evaluate the dynamic behavior of power devices under a range of conditions, whether to optimize devices or confirm the actual value or deviation of power devices and modules. The double pulse test is a test method to measure the switching parameters and evaluate the dynamic behaviors of power devices, and typically for these kinds of parameters. So for turn on, the rise time, delay, dVdt and dIdt. For turn off, the fall time, the delay, and the turn off time, and dIdt and dVdt. And the reverse recovery parameters, which would be the reverse recovery time, reverse recovery current, dIdt, and VDS. Now, when you're setting up the equipment for making this test, You typically do this with a scope. With a single-ended probe, a lot of times you see people say that you need to use a differential probe, but that's not really the case. Usually a single-ended probe with the sufficient bandwidth is enough. A current probe and an accurate signal source. Some final measurement challenges are being able to do EMI pre-compliance and debugging. High slew rates, either DVDT or DIDT, cause ringing and unwanted noise and emissions. It's become such an important topic that industry experts believe a barrier to adoption for silicon carbide is proving that it doesn't have much higher noise compared to silicon. Characterizing EMI in a power system for pre-compliance testing using sound debugging techniques through an oscilloscope and/or a spectrum analyzer are critical, especially if these problems can be uncovered in the early design stages. An oscilloscope with a set of near-field probes is useful for locating EMC problems on circuit boards, integrated circuits, cables, and shielding, and it's an ideal tool for emission measurements from 30 megahertz to around 3 gigahertz. A primary benefit of a scope is it can transform signals from the time domain into the frequency domain using FFT. The key parameters for an oscilloscope to be useful for EMI applications are low front-end noise with sufficient dynamic range for weaker emissions, direct input of frequency parameters such as start and stop frequency or resolution bandwidth, and fast and efficient FFT analysis, which is particularly important for near-field probing since immediate feedback about the noise level at a specific location is important. For EMI compliance tests up to 3 gigahertz, Rohde & Schwarz offers a portfolio of instruments dedicated to cost-efficient EMI testing and debugging, including the RTM3000 with an HZ15 probe set. Shown is a spectral measurement on the RTM3000. The time domain waveform is on top of the screen, showing the triggers and noise chirp. At the bottom is the current FFT, and the spectrogram records all the previous spectral magnitude. A particularly useful feature of the EMI testing with an oscilloscope is correlating time frequency analysis to reveal how the signal spectrum evolves over time. This method is used where multiple broadband sources exist, so for example, switch mode power supplies with DC level converters. The following oscilloscope analysis tools are beneficial for EMI testing. FFT gating emissions. So by applying FFT gating, you can see how the spectra evolves over time. This is useful for switching events in switch mode power supplies. FFT gating also isolates spurious spectral components in the time domain. Another thing is correlated interface sources analysis. Embedded RF designs require complex test setups in order to examine their behavior, which is why an oscilloscope with time-correlated measurement across multiple domains is an invaluable tool. And finally, a history function for the emissions analysis is important. All previously captured signals are stored in memory and can be accessed as required. With a timestamp, it is easier to find correlation. All safe signals can be further analyzed with options such as zoom, measurement, math, and spectrum analysis. Newly acquired signals can be quickly compared with ones previously stored in memory. Radiated emissions are inherent to any electrical circuit. A spectrum analyzer is an excellent tool for designers to measure the electromagnetic field strength of unintentional emissions generated by your products. A standard requirement for power quality includes testing for harmonics. Unwanted harmonics increase the heat generated in the electrical system, leading to losses, greater costs, as well as reduced performance of the system itself. Limiting the harmonics is an important task. For debugging and locating emission sources using a spectrum analyzer, Rohde & Schwarz offers the FPC1000 and FPC1500 spectrum analyzers, which offer outstanding performance. Together with the HZ17 near-field probe set, this is an excellent tool used for locating the source in EMI debugging. The Rohde & Schwarz HZ16 preamplifier improves measurement sensitivity up to 3 gigahertz with approximately 20 dB gain and a noise figure of 4.5 dB. Thank you for attending today's webinar on half-bridge and gate drive measurements and how to use proper measurement techniques when making these measurements. If you need additional information, you can find it on the Rohde & Schwarz website.